Hi, welcome to this lecture on this hypothetical machine called the Harvey Mud Miniature Machine, or HMMM for short. We're going to discuss the architecture of this machine, and we will also talk about the assembly language, also called HMMM, that you use to talk to this machine. So here's an outline for this lecture. We will talk about the HMMM architecture, and then we will talk about a very simple HMMM program, a program that is written in the HMMM assembly language. And then we will talk about how you perform looping in HMMM, and then we will discuss how you implement functions in HMMM, and then we'll talk about a particular kind of function called a recursive function, and then finally we'll summarize the entire HMMM instruction set. So let's get started. Now, a real computer needs to be able to move information between registers and memory. We discussed this in the last lecture. We said that a computer typically consists of a central processing unit and also the main memory, and that it needs to be able to move information back and forth between the CPU and the memory, right? And it's the CPU that consists of registers, program counter, instruction register, and so on. And in addition, a real computer must also be capable of getting data from the outside world, meaning it needs to be able to receive user input. It also needs to be able to produce meaningful output, such as print results and so on. And then finally, it needs to be able to make decisions. All right. Now, this machine called the Harvey Mud Miniature Machine, or HMMM for short, is organized as follows. Both instructions and data on this computer are going to be represented using 16-bit numbers. All right? Unlike the simple computer that we considered in the previous lecture, where things were 8-bit wide. In addition to the program counter and the instruction register, which are the two special registers that we talked about in the last lecture, there are 16 registers which are labeled R0 through R15, right? So there are 16 registers in all at your disposal, and these are given labels R0 through R15. Now, some of them are special, and we'll talk about these later on. There are also 256 memory locations. Okay, so the main memory on this computer has 256 memory locations. Now, as we mentioned in the last lecture, we don't want to be writing code in binary, meaning we don't want to be writing programs in zeros and ones. Instead, we want to be writing our programs at a higher level. So what we will use here is an assembly language called HMMM, which is a programming language where each instruction has a symbolic representation, right? Which is much easier to work with. For example, let's say we want to take the values in registers R1 and R2 and store the result of their sum in the register R3, meaning we want to calculate something like R3 equals R1 plus R2. So we would express that computation in our assembly language program by writing something like add R3, R1, R2, which means we want to add the values in registers R1 and R2 and store the result in the register R3. Okay, so we will be writing our code using this symbolic representation, right, and not in zeros and ones. Now, once we have our program written in the assembly language, what we will do is we'll use a program to convert the assembly language code into a program that contains zeros and ones, which is the machine language, right? And it's the machine language program that the computer knows how to execute. Okay, so we won't be writing code in zeros and ones. We will be writing code using symbolic instructions, and then we will translate that using a program into machine code, which we will then run on the computer. Now, there are Two simulation environments that are available to run or to assemble and run HMMM programs. And by simulation environments, what we mean is it's basically an environment where you can test your HMMM programs. All right. So the first one is an online simulator, and it's available at this website. And if you go to that website, you will see an interface that looks like this. All right. On the left hand side, you can enter, you can type, or you can load an HMMM program. And once you're done with that, you can press this assemble button. And when you do that, what you see on the right hand side is the machine language program, okay, corresponding to this assembly language program. So that's the assembly step. So you assemble this HMMM program into machine code by just pushing this button, right? And once you have this, assuming that there's no error in the program that you wrote, what you can do is you can click the simulate button, and when you do that, you see this particular user interface, right? And what you're seeing here on the left hand side is the CPU of HMMM, listing all the registers, including the program register counter and the instruction register. And what you're seeing on the right hand side is the main memory, all right, or the RAM of HMMM. There are 256 memory locations. And then in here, what you see is the output of the program. So if you want to run this program, you simply push the run button, and what that does is it asks for user input, if any, and then it simply executes the program and produces the desired output, which you will see in this small window. Okay, so that's a nice environment that you could use to simulate your HMMM programs. There is another environment which is entirely terminal based, and that can be obtained from this website here. And the terminal based simulator consists of two things. So you first assemble your HMMM program, for example my_program.hmmm, into a machine language program my_program.b, b for binary, by running this this command on the terminal. Okay, so you simply launch the terminal, go into the folder that contains your HMMM program, and simply run this command. So what you're doing here is you're invoking the assembler program, which is a Python script, and hence you say Python here. So you invoke this assembler program to translate your input HMMM program into the output machine language program. Okay, so -f for input and -o for output. So this is in HMMM, and this is the output machine language program. Okay, now once you have assembled, assuming that your programs did not have any errors in it, what you can do is you can simulate or run the binary program. And the way you do that is by running this command on the terminal. So here you invoke the Python program called HMMM simulator, okay, to simulate or run your program my_program.b, which was produced by this step. And so that's your input now, -f. And then you also specify this flag -n, meaning, you know, running in no debug mode. All right. So when you do this, the simulator simply runs this program. It will ask for any input that it might need, and then it'll produce the desired output. Okay, so that's how you do things on the terminal. You first assemble your program, and then you run it. All right, it's a two-step process. Okay, so now let's start looking at some HMMM programs. Okay, so we'll start with a very simple program that is called triangle1.hmmm. And this is an example of what we call a straight line program, meaning it just executes top to bottom in a linear fashion, one instruction at a time, right? And what this program does is it calculates the approximate area of a triangle. And I'll explain in a bit as to why it's approximate and not exact. Okay, so here is the program. It's HMMM program. It's written in a file that's called triangle1.hmmm. So what are the things that you see here? Well, the very first column is basically the instruction number, and that's simply a sequence of numbers starting at 0 and going all the way up to 6 in this case. All right, so the first column is simply the instruction number. The next column is the instruction. All right, that's the instruction that you want to carry out. And then the other columns represent any inputs and outputs corresponding to those instructions. Okay, and then anything that starts with a hash sign is a comment, and that's simply something that is completely ignored by the assembler. Comments exist only for human consumption. It's basically for readability, just so someone reading your code can understand or follow what you're trying to say. Okay, so those are the broadly speaking, those are the things that you see in this code: instruction number, instructions, input and output, information, and then comments. All right. Okay, so now let's walk through each and every instruction here in order. So the very first instruction, which starts with the instruction number 0, is the read instruction. Okay, and this is the instruction that you use to read an input from the outside world, from the user. Okay, and the way this works is, when the instruction is executed, it reads a number into the register that you specify here. All right, in this case, it's the register R1. And we're going to treat this value as being the base of the triangle for which we want to calculate the area. So we get the base of the triangle from the user and store it in the register R1. All right, and then the next instruction is to read the height of the triangle. Okay, and that we store in the register R2. So once these two instructions are done, we have our two inputs, the base and height, stored in the registers R1 and R2 respectively. Now the next thing that we do is we have the multiplication instruction, and the way that works is it multiplies the values in registers R1 and R2, meaning the base and height, and stores the result, base times height, in the register R1. All right, so we are simply calculating base times height into R1 as it is denoted by, as is indicated by this comment here. Okay, so for example, if, let's say for the sake of argument, that the base was 5 and then the height was 4. So the value in R1 is 5, the value in R2 is 4, and then once the multiplication instruction is executed, the value in R1 now is R1 times R2, which is 20. So R1 now contains 20. So it has lost information about what used to be in R1, which is on the base of the triangle, but we don't need that anymore. Okay, so now the new value in R1 is base times height, which is 20. What is the next instruction? The next instruction says set the register R2 with the constant 2. That's how setn works. It takes two inputs, a register number and the number, and that number is stored in that register. Okay, so here we are simply storing the constant 2 in the register R2. The next instruction says divide the value in R1 by the value in R2 and store the result in R1. Well, what was in R1? R1 had the value 20. What is in R2? 2. So 20 divided by 2 is 10, and that's the value that is stored in R1. Okay. So what is this? This is basically half base times height. Right? And that is the area of the triangle whose base is b and height is h. And then what we do is we simply write the value in register R1 as the output. So that simply writes 10 to the terminal, and then we halt the machine, we halt the program. Okay? So that's it. It's a very simple program that calculates the area of a triangle where the inputs, the base and height, are provided from the outside world by the user. So let's see how we run this program. Well, the first step is to assemble it. So what we do is on the terminal, within the directory that contains this program triangle1.hmmm, what we do is we run the assembler program. Okay, so we assemble the input program triangle1.hmmm. So this is the input, which is this program here, into the output machine language program triangle1.b. Okay, and when you do this on the screen, you will see something like this. You'll see an output like this. So what are we looking at here? Well, on the left hand side, what you see is the binary, the machine code. So all this is the machine code equivalent of this program. Okay, and what you see here is the HMMM program itself. All right, and now I hope you guys sort of appreciate the fact that you are writing your program at this level and not at this level. Okay? It's incredibly tedious to write the program at this level. So we would rather write it at this level and have it automatically translated into this code, which is what we did by this command. Okay. Now, if assuming that there are no errors in this program, and this program is actually is quite error-free, what you can do next is actually run this machine language program. Okay, and that's and the way you do that is by running the simulator program. Okay, so we run the simulator program on the input triangle1.b. So this is now the input, and this was generated by the assembler as the output. Okay, so that's now the input to the simulator, and we also specify this -n for no debug. So we run the program in no debug mode. So when you do that, once you run this command and hit enter, the program will just wait there for input. Okay? So what you do is you first type your first input. So in this case it is 4 for base, and that's the value that is stored in R1. Okay, and then the program waits for another input because it needs the height of the triangle. So you type in a 5, which is stored in R2, and then once you type 5 and hit enter, the program simply calculates the area of the triangle as 10 and prints it out. So those were the rest of the instructions that we discussed before. Okay, now before we proceed, I just want to mention one thing, which is that the area that we calculate here is approximate. Why is that? Well, if, for example, the base of the triangle were supplied as 3 and the height as 5, the height, let's say, of 4, let's keep it at 5. Okay, so the base is 3 and height is 5. What is the area of the triangle? Well, actually the area of this triangle is half times base times height, which is 7.5. But this program will print the area as 7 and not 7.5. And why is that? Well, that is because HMMM does not support floating point numbers. Okay, so it only supports integers. So any result that is a floating point number is rounded down. So 7.5 is simply printed as 7, and hence we say that it calculates the approximate area of a triangle, not the true area. Okay, so just keep this in mind that HMMM only supports integers. Okay, so that's our very first HMMM program. It's a simple straight line program that executes top to bottom one instruction at a time. All right. Now, let's say we want to write another version of this triangle program where we want to calculate the area of the triangle not just once, but many, many, many times. How do we do that? Well, that brings us to the notion of looping. Okay, and we achieve looping via what are called jump instructions. Now, the very first jump instruction that we're going to consider is an unconditional jump. And the way that works is you put the instruction name, which is jump n, and then you specify the instruction number where you want to jump to. Okay, and when this instruction is executed, the control is transferred immediately to the instruction whose number is given by n. All right, and since this jump is not based on any condition, we call this an unconditional jump. Right? So what is going on internally is when this instruction is executed, the program counter register is simply set to this number. So the next instruction that is executed is simply the instruction that has this as the instruction number. Okay. So let's now look at a different version of the triangle program. It's called triangle2.hmmm that calculates the approximate areas of many triangles, not just one. All right. So it's just a slight modification of the previous program. So let's go through this in sequence. So the very first instruction that you see is the read instruction, just like before, that reads the base of the triangle in register R1. And then you have a read instruction that reads the height of the triangle in R2. Then we calculate base times height in register R1, just like before. Then we store the constant 2 in register R2. Then we divide R1, which had base times height in it, by R2, which has the number 2, and we store the result in R1. So R1 has the result, the area of the triangle. And then we simply write the area of the triangle. We write R1. Okay? But then we do something interesting. Once that is done, we do an unconditional jump. We make use of this instruction here. We make an unconditional jump to instruction number 0. But what is instruction number 0? Well, it's this very first instruction. So from here, we unconditionally jump here. And what do we do then? Well, we repeat the whole process of getting the base and height of another triangle, calculating and printing its area. And once that is done, what we do again? Again, we loop unconditionally. We jump unconditionally to instruction 0, carry this all over again. So as you can see, this program just indefinitely keeps calculating the areas of many triangles, one after the other. Okay. Now, how do we run this? Well, remember that the first thing that you need to do is assemble the program. So, and I have suppressed that step here, but let's assume that you've assembled it. You've assembled triangle2.hmmm into triangle2.b. Once you've done that, you can simulate triangle2.b using this command. And when you do that, the program expects for 2 inputs, base and height, which you supply as 4 and 5, and the program comes back with the output 10, the area of the triangle. Then it goes back and repeats the process. It expects another set of values for base and height. You type 5 and 5, the program comes back with 12 as the area. Okay. Notice it's the approximate area. It's not 12.5, which is the real area. Okay. All right. And then it'll keep doing this over and over. Okay, but what if you want to stop the process? Let's say you're done calculating area. So what do? Well, you can terminate the program by typing a key combination Control D. So you hit both Control and D at the same time. That terminates the program. Okay, but when you do so, you get, the program surely terminates, meaning it stops calculating areas of triangles, but it does come back with this, this nasty message, okay? And this, we would say, is not very graceful, all right? So what we want to do is, we want to write a program that terminates gracefully without any such, spurious messages. And that's what we're going to discuss next. We're going to write another version of the triangle program where we will be able to calculate the areas of many triangles, but at the same time, we'll also be able to terminate the program in a graceful manner, all right, where we don't see any such nasty messages. Okay, and that will bring us to the notion of a conditional jump. So that's what we will discuss next. So there are several forms of the conditional jump instruction. Here is one particular form. So the instruction is called JEQZN, and then it has 2 inputs. You specify a register number, and then you also specify an instruction number. And the way this instruction works is it checks if this register has a value that is identically 0. And if it is, then we jump to this instruction number n. Otherwise, it's the following instruction that is executed. Right? So that's why it's called a conditional jump. We jump to this instruction only if this register has the value 0. And if it does not, we simply carry on with the immediately following instruction. Okay, so that's how this conditional jump instruction works. So let's see how we can put this to use in implementing this version, the third version of our triangle program, that also calculates the approximate areas of many triangles, but gracefully stops when either the base or the height is identically 0. Okay, so if one of the two inputs, base or height, is 0, then we assume that the user is done calculating areas, and the program will gracefully halt. Okay, so let's see how we implement this in code. Okay, so the very first instruction is getting the base from the user and storing it in register R1. And then we have one of these conditional jump instructions. Okay, and what are we saying there? Well, we're saying if the value of the register R1, meaning if the base is 0, then simply jump to instruction 9. What is instruction 9? It is halt. So we're saying if the base is 0, just halt the program, right? But if R1 or the base is not 0, then it's the next instruction that is executed. And what do we do there? Well, we get the height in R2, just like before. And then we check again using this conditional jump instruction to see if R2 is identically 0. And if so, we again halt the program by jumping to instruction 9, which is the halt instruction. Okay, and if height is not 0 either, what do we do? Well, as before, we calculate base times height in R1. We store the constant 2 in R2. We divide base times height by 2 and store the result in R1. So that's now the area, and we write the area. And then comes the unconditional jump to 0. So from here we simply go back so that we can calculate the area of another triangle. All right, so this program can calculate the areas of many triangles, and at the same time it can very nicely halt gracefully when either the base or the height is 0. Okay, so this is a very nice program that illustrates both a conditional and an unconditional jump. So here again, the first step is to assemble the program, which we have suppressed here. But once the program is assembled to a machine language program called Triangle 3B, then we can simulate that by running the HMMM simulator program, okay, with triangle 3.b as the input. And when we do that, the program waits for input. We supply base and height, 4 and 5. The program comes back with 10 as the output. And then supply base and height for another triangle. The program comes back with 12 as the output. And then let's say we are done and we simply type 0 for base. Okay, and since R1 was 0, and when this instruction is executed, R1 is indeed 0, so we end up jumping to 9, and 9 simply halts the program. Okay, and we are done. And notice that there was no crazy message that was printed, so the program has gracefully stopped. All right, and this is what we should always aim to do when we write our programs. Our program should always behave in a graceful manner. Even when there is an error, it should exit the program gracefully or report some nice error message and then move on. Okay, all right. The next concept to discuss is that of a function. Okay. Now, before we talk about the instructions that we use to set up a function in HMMM, let me give you a motivation for functions. So let's say you have, you have an HMMM program where you have a few instructions that compute some function, let's say f, right? And then later on, you perform the same computation. You compute the same function again, f, and then let's say you do the same thing again, and then again, and so on. So this is now a very untidy way of organizing your code, and not to mention it's also quite error prone, because what if you realize that the logic that you had in here was flawed, and you go about fixing it. So you fix it, let's say here, you fix it here, and then for some reason you just forget to fix it here and you fix it here. All right, so since the same logic appears in so many places. It's very easy to sort of forget the fix in one of the places. Okay, so a code written in this fashion is not quite maintainable. Instead, what you do in a program is as follows. You extract the common functionality out into a region of the program that we call a function. So you have one region of the code which is some designated function, and that is just done once. It's written once in the program. And then in your main part of the program, whenever you need access to that function, you simply call it. All right? You simply call, and control is transferred to that function at that point, and then the function does its job, computes something, and returns the result back to the caller. Okay, and then let's say later on you need that same functionality again. Well, you simply call the function again. That simply calls this guy, and this guy simply computes the value and returns it, and so on. So you can have any number of such calls to the function, and so on. So notice that the function definition shows up just once in the program. So if there is any problem with your function, you fix it exactly in one place, not in multiple places. Okay. So this program, a program written like this in the form of like a main part and a function part, is much more maintainable, right, than a program that is written without functions. So that's basically the motivation for a function. If you need the same functionality over and over again in a program, you simply define that functionality as a function, and you simply call that function when that functionality is needed. Okay. So how do we work with functions in HMMM? Well, you make use of a couple of instructions. The first instruction that you need is the call-n instruction. Okay, so call-n has two inputs. It specifies a register number, and it also specifies an instruction number. Okay, now the way call-n works is it stores the instruction number that immediately follows call-n in Rx, in this register. Okay, and then it jumps to the function whose definition starts at n. So that's how call-n works. The number of the instruction that immediately follows call-n is stored in this register, and a jump is made to instruction that has n as the instruction number. That's where the function is defined. Okay. Now, the value that is stored in Rx is what we call the return address. And that is basically, as I said before, it is the following instruction. And that makes sense, right? Because when the function that you're calling, when it returns back to the caller, it's the following instruction that needs to be executed next. It's the instruction that follows call-in. Okay, so that is the return address. So let me give you an example. So let's say, in your program, as instruction 10, you have the call-n instruction, and then Rx is some register number R14, and then let's say your function definition starts at instruction 17. Okay, so at 17 you have your function definition. Okay, now when this instruction is executed, what is the value of R14? Well, it is 11. So there's some instruction here, and it is 11 that is stored in R14. Okay, and a jump is made to the instruction 17, which is where your function starts, and the function goes about doing its own thing, and at some point the function will have an instruction called jump R14, and that's an unconditional jump to the return address which is stored in R14, and that has the effect of jumping back to this instruction because 11 is what was stored in R15. Okay, so call-n calls a function, and then jump R transfers control back to the caller by making a jump to the return address. Okay, So that's basically how Colin works. So as I just said, in order to return from a function, you make use of the unconditional jump instruction jump R, specifying the register that contains the return address. Okay. Now, by convention, we are going to use the register R14 to store the return address. So that's a convention that we follow. So in Colin, Rx will always be R14, and when a function returns control to the caller, the register that you use along with jump R is always going to be R14 by convention. Okay, so we're going to reserve R14 for return address. So let's look at an example of an HMMM program where we organize things using function. So this program is extremely simple, and it's called square.hmmm. What it does is it calculates the square of an input number n. So here's the program. It's organized in two parts. There is the main part, and then there is the function part. All right. And what does the main part do? Well, the main part reads an input, the number n, into register R1, and then what it does is it makes a call to a function whose definition starts at 5. And here is that function. Okay, what does this function do? Well, this function is the one that calculates the square of a number and returns control back to the caller. Okay, so this function expects the input to be in R1, so n is in R1, and then it places the result n square in R2. So the square of n is placed in R2. Okay, so the implementation of the function is extremely straightforward. It simply takes the value of R1, multiplies that with itself, and stores the result in R2 and jumps back to the caller. It jumps unconditionally to R14, which has the return address. Okay, so let's go through this and see how this works. So let's say we read a value from the user, and let's say this value was 5. So R1 is 5, right? And then we have the Colin instruction, and the way that works is since the instruction that follows Colin is instruction number 2, R14 contains the value 2. Okay? And then we jump to the instruction, the function definition, which starts at 5. So we are here. But what is R1 at this point? R1 is the input 5. So we multiply 5 and 5 and store the result in R2. So R2 is now 25. Okay. And then we jump to R14. But what was in R14? It was the value 2. So we are back here and we write the value of R2. But what is in R2? Well, R2 has the result 25. So this ends up writing the value 25. That's the result, square of 5. And then we simply halt the program. Okay? And this no-op instruction has no effect whatsoever. It's basically used as a filler. So if there is like a gap between the main part and the function, you just fill in with a bunch of no-op instructions, because there cannot be like a gap in instruction number, you see. So if we need a filler, we simply use the no-op instruction, right? But the no-op instruction does nothing. Okay. All right. So that's our first example where we organize things using functions. Now this program really didn't sort of like need a function, because we just need the square of a number calculated in one place. But nevertheless, it shows how you work with functions in HMMM. The next program that we will see sort of makes this case for a function very nicely. All right. But before we do that, let's see how this program behaves when you run it. So as usual, remember to first assemble it And then once it's assembled to a machine language program called square.b, you can run that using this command. And when you do that, the program expects a single input. Let's say you type 11, and then the program comes back with the square of that number, which is 121. Okay, let's look at another program. This one is called combinations.hmmm. And what this program does is it calculates what is called n choose k. All right? So C n comma k is also called n choose k, and it's basically a number that tells you in how many ways you can select k items from n items, where the ordering is irrelevant. All right? So for example, if n is 3, so let's say there are 3 items A, B, and C, and let's say k is 2. So the question is, in how many ways can you select 2 items from 3 items where the ordering is irrelevant? Well, there are 3 ways in which you can do this. You can select AB, you can select BC, you can select AC. Okay, so C and K is basically the number of ways in which you choose k items from n items where order doesn't matter. And this has a nice formula. It is written as n factorial divided by k factorial times n minus k factorial. Now, what is the factorial of a number? Well, n factorial is given by this expression here. All right, it's basically n times n minus 1 and so on, all the way down to 2 times 1, and 0 factorial by definition is 1. Okay, so for example, what is 3 factorial? Well, it is 3 times 2 times 1, which is 6. What is 2 factorial? It is 2 times 1, which is 2. And what is 1 factorial? Well, that's simply 1. So what then is C3, 2? Meaning, in how many ways can you select 2 items from 3 items? Well, going by the formula, it is n factorial, which is 3 factorial, divided by k factorial, which is 2 factorial, times n minus k factorial, which is 3 minus 2, or 1 factorial. But what is this? 6 divided by 2 times 1, which is 3. All right, and that's exactly what we saw here. 3 ways of selecting 2 items from a collection of 3 items. Okay. All right. So what does this program do? Well, this program takes 2 inputs, n and k, and it simply prints n choose k. So if n is 3 and k is 2, it's going to print 3. Right? And let's see how it works. Now here, notice that we need the factorial of a number calculated 3 times. All right, we first need it for n factorial, then we need it for k factorial, and then we need it for n minus k factorial. So we're going to need the factorial functionality 3 times in this program. So here, it makes no sense to repeat the logic for calculating factorial 3 times. Instead, it makes much more sense to define the factorial function just once, which is what is done here, and then just call that function when you need the functionality. Okay, and that's exactly what we will see in the code. So let's go through this carefully. We first read a user input n into register R3. And then we read k into the register R4. Okay, those are the 2 inputs. And then we simply store the value of R3 in register R1 using the copy instruction. So copy simply copies the value in this register to the value in that register. Now, why are we doing this? Well, this function here that calculates the factorial of a number expects its input to be in R1. So that's input. And it places the result, meaning n factorial, in R2. Okay, so R2 is going to contain n factorial. So from here, if we need the factorial functionality, we better place the input in the register R1 because that's where the function expects it to be. Okay, that's what we're doing. We're storing n in R1. Okay, because n was in R3. We're storing it in R1, copying it into R1, and then comes the function call. We make a call to the function, factorial function, whose definition is at 15. Now notice that when you do this, what is the value of R14? It is the very next instruction, 4. So 4 is stored in R14. And then what does this function do? It calculates the factorial of a number and it places the result in R2. We'll look at this function later on, but for now assume that it does the job, meaning it places the result in R2. So, and then it jumps back to the caller, but where is it going to jump back? Well, the instruction right after call n, okay, which is this instruction here, all right? Because from the function, when we do a jump R14, what was the value of R14? It was 4. So this is where we end up. And what are we doing there? We are saving the value of R2 in R5. But what's in R2? Well, the function just calculated the factorial of a number in R2. So, so R2 at this point is basically n factorial. So n factorial is now saved away in R5. All right. So R5 at this point is going to contain n factorial. Okay, now what next? The next thing that we do is copy the value of R4, which was k, into the register R1. Why are we doing this? Because the next thing we need to do is calculate k factorial, which is this part. Okay, so we do that, we copy k into R1, and then we simply make another call to the factorial function. But at this point, what is going to be the value of R14? Very next instruction, which is 7. So R14 is 7 now. Okay, and then the factorial function calculates the value of the factorial of a number in R1, which was k, as k factorial, which is placed in R2. So, and the function transfers control back to this line, which is the line right after call n. And what are we doing there? Well, we divide what is in R5, which was n factorial, by what is in R2, which is k factorial, and we store the result back in R5. So once instruction number 7 is executed, R5 is going to be n factorial divided by k factorial. So what we have managed to calculate so far is this part of the formula. All that we need to do is calculate this part, and that's what we do next. Okay. We subtract the value in R4 from the value in R3. So we are basically doing n minus k, and we are storing the result in R1. So R1 now contains n minus k. Why are we doing that? Because we need to calculate n minus k factorial next. So we call the factorial function one last time. And at this point, R14 is going to contain the value 10, because that's the very next instruction. And factorial function calculates the factorial of n minus k and places the result in R2 and transfers control back to this instruction here. And what are we doing? We are taking the value in R5, which is that so far, and we are dividing that by the value in R2, which was just calculated as n minus k factorial. So once this division instruction is done, what is in R5 is precisely the overall thing that we want, n factorial divided by k factorial times n minus k factorial. Okay, and that's the result that we write in the very next instruction. Okay, and then we halt the program, and then we have a couple of filler instructions, the no-op instructions. Okay, so that's how the main part works. And as you can see, it made use of the factorial functionality 3 times. All right. Now let's talk about how the factorial function works and how that is implemented. So the input is in R1, that's n, and the output is in R2. Okay, that's n factorial. Okay, so the first thing that we do is we store the constant 1 in the register R2, the result register. And then we check if the input register is 0 or not using this conditional jump instruction. And if it is 0, we simply jump to 20, which is this line here. And from here, we jump back to the caller. Okay. But if R1 is not 0, then what we do is in the next line, we simply take the current value of R1, multiply it with R2, and store the result back in R2. Okay, and then once that is done, we decrement R1 by 1. So that's what the add-in instruction does with a negative number as the second argument. We decrement the value of R1 by 1, and then we make an unconditional jump back to 16, which is this line here, which checks again if R1 is 0 or not. And if it is still not 0, it's going to take the current value of R1, multiply it by R2, and store the result back in R2, decrement the value of R1 by 1, and do an unconditional jump. Okay. As you can see, since we are constantly decrementing R1, at some point this condition is going to be true, meaning R1 is going to be precisely 0, in which case you jump to 20 and you're back to the caller. Okay, so as you can see, this factorial function eventually terminates. Okay, and when it does, it has the value of n factorial in the register R2. Okay. Okay, so that's the factorial function, and in the next slide we're going to look at a trace of this factorial function. Okay, for now let's see some input and output. So let's say we first assemble the program into combinations.b, and we assimilate combinations.b using this command. When you do that, the program expects two inputs. So in this case, our n was 5 and k was 2. So in how many ways can you select 2 items from 5 items? The program comes back with the result 10. And that is correct, because C of 5 choose 2 is basically 5 factorial divided by k factorial, which is 2 factorial, times 5 minus 2 factorial. Okay, what is this? Well, you can convince yourself that the numerator is 120, the denominator is a 2 times 6, and this is precisely 10. Okay, all right, so that's how this program works. Now let's look at a trace of the factorial function for a small value of input, which is n equals 4. So let's see how the function calculates the factorial of 4. Okay, now what is factorial of 4? Well, 4 factorial is simply 4 times 3 times 2 times 1, and that is 24. So we ought to get this as the result in the register R2. Okay. All right, so we call the function, the factorial function, which is what is shown here, with the value 4 in the register R1, because the function expects the input to be in register R1. So that's what we have. So n is 4. So what happens next? Well, the first instruction says set R2 to the value 1, and that's what you see here. The next instruction checks the value of R1 and sees if it is 0 or not. Well, it is not 0, right? So we simply execute the very next instruction, because R1 is not 0. And what is the next instruction? Well, it takes the current value of R1, which is 4, and the current value of R2, which is 1, multiplies the two together and places the result in R2. That's how you have R2 equals 4. The next instruction is decrement the value of R1 by 1. So R1 was 4, it now becomes 3. The next instruction is an unconditional jump to 16. Okay, so the next instruction that is executed is instruction number 16. We again check if R1 is 0 or not. It's not 0, so it's 17 that gets executed next. We multiply the current values of R1 and R2, which is 3 and 4, to get 12, and that result is placed in R2, so that's why R2 is 12. Then we decrement R1 by 1 to get 2. It goes from 3 to 2. Then we unconditionally jump to 16. We check if R1 is 0 or not. Well, it is not 0, it is 2. we multiply R1 and R2 and store the result in R2. So 2 times 12 is we get 24, which is stored in R2. Then we decrement R1 by 1 to get 1, goes from 2 to 1. And then unconditional jump again to 16. We check if R1 is 0 or not. Well, it's not. So we do multiply R1 and R2, 1 and 24, and place the result 24 in R2. And then R1 is decremented again. It goes from 1 to 0. And then we do an unconditional jump again to 16. And now when we check R1 against 0, well, they are the same. R1 has the value 0. So in that case, we jump to instruction number 20. That's the that's the next instruction that's executed. And what does that instruction do? Well, it jumps back to the caller, the return address that is stored in R14. But when it does that, when it jumps out of the function into the caller, what is the current value in R2? Well, it's 24, and that is precisely 4 factorial, okay, which we calculated here above. So this function correctly calculates the factorial of a number and places that result in R2, okay. All right. So now what we are going to do is talk about a very special kind of a function called a recursive function, all right? And see how recursive functions are implemented in HMMM. So what is a recursive function? A recursive function is a function that calls itself on smaller inputs, okay? And it has what is called a base case, because that's what makes sure that the recursion terminates. So let's take an example of the factorial function again and look at it as a recursive function. Okay. So what is n factorial? Well, n factorial, remember, is n times n minus 1 times n minus 2 and so on down to 1 and down to 2 and 1. Okay. And then 0 factorial by definition is 1. All right. Now, if you focus on this part of the formula, what can we say about that part? Well, that part is precisely n minus 1 factorial. Okay, so that's why we are able to express n factorial as n times n minus 1 factorial. Okay, and this is basically the recursive step. Meaning the factorial function calls the factorial function again. But notice that the call is on a smaller input. On the left hand side, factorial was called on n, whereas on the right hand side, factorial is called on n minus 1. So that's what we are talking about here. A recursive function is a function that calls itself on smaller inputs. Okay, and then what can you say about n minus 1 factorial? Well, that in itself can be written as n minus 1 times n minus 2 factorial. Okay, so as you can see, these inputs get smaller and smaller and smaller, and at some point it is going to, since it's constantly decreasing, it's going to become 0 at some point, and that's when we hit the base case, because n at that point is 0, and there we terminate the recursion and we say that factorial of 0 is simply 1. Okay. So let's take a concrete example. Let's look at 5 factorial. So 5 factorial means n is 5. Okay, so n is not 0 in this case, it is greater than 0. So this is going to be 5 times 4 factorial. Okay, now what about 4 factorial? Well, here n is 4, which is greater than 0. So this is going to result in 4 times 3 factorial. What about 3? That is going to result in 3 times 2 factorial. What is 2? That is going to result in 2 times 1 factorial. What is 1? That's going to result in 1 times 0 factorial. But now notice that at this stage n is 0, So this whole thing from the base case simply evaluates to 1. Right? That's the base case. Now, since 1 times 1 is 1, this whole thing now is a 1. And 2 times 1 is a 2, so this whole thing is a 2. And 3 times 2 is a 6, so this whole thing is a 6. Now 4 times 6 is a 24, so this whole thing is a 24. And then 5 times 4 is 120, so 5 factorial is basically 120. Okay? Alright, so that's how recursion works. So now we're going to talk about how you do a recursion in HMMM. But for that, we need the notion of a stack. Now, a stack is a storage mechanism or a data structure that remembers things and gives them back in reverse order. It's sort of like, like stacking a bunch of plates on top of one another. Okay, so when you pile up plates on top of each other, and then later on, if you go to grab a plate, what's the plate that you get? Well, it's the plate that went in the last. Okay, so so you take a bunch of plates and just stack them on top of one another, and then when you go reach out for a plate, it's this one that you get. That's the top of the stack. Okay. So the last thing that went in is the first thing that comes out, and then if you go grab another plate, it's the next one that comes in. Okay, so the stack has a very interesting property in that it implements this last in, first out, or a LIFO idea. Okay, so last thing that goes in is the first thing that comes out. Okay, so that's what a stack is. And now to implement a stack on a computer, we need what is called a stack pointer, okay? Which is a register that holds the memory address of the top item on the stack, all right? So think of this as your memory, all right? And let's say this memory cell is the top of the stack, okay? So that's the top. And let's say the bottom of the stack is somewhere here. So the stack grows in this direction, all right? Now, the stack pointer is basically a register. So stack pointer is a register that points to the top of the stack, all right? And we are going to use the register R15 as the stack pointer. So R15 for us by convention is going to store the stack pointer, meaning it's going to store the location in memory that has the top of the stack. All right, so keep that in mind. All right, now what you're seeing next is some code to push something, say the contents of register 4 on top of the stack. All right, so let's say you have some value in R4, for example, the value 5, and you want to push it on top of the stack. So what do? Well, you have your memory, and then you have R15, the stack pointer, pointing to some location in memory. All right? So the first thing so now you want to store this register value on top of the stack. So the first thing that you do is you increment the stack pointer by 1. So now the stack pointer is not pointing to that, but it's pointing to the next cell. Okay, that's what this line here achieves. Increment the stack pointer by 1. Okay, so initially if it was, let's say, 100, now it becomes 101. Right, and at that location, what you do is you store the value of R4 into the location that is given by the stack pointer. Okay, so store R is an instruction that takes a value of a register and stores it in the address that is given by this register. Okay, so here it's the stack pointer. So we simply take whatever is in R4, which was 5, and store it at this location. Okay, so that's how you push something on top of the stack. You increment the stack pointer and you store some value at that location. Now, what about the other way around? Let's say you want to recover something from the top of the stack into some register. So let's say you want to recover the top of the stack into the register R3. So here it is, some memory location 100, and then you have 101. That's where we stored this value, right? And so the stack pointer basically points to that one, right? So let's say we want to recover this value into some register R3. So what do? Well, we first execute this instruction called load R, which is the reverse of store R, that takes the value in memory given by this location. So R15 now contains 101. So we get this value 5 into the register R3. So R3 is now 5. And then we add -1 to R15, meaning we decrement the stack pointer by 1. So once this value is fetched, we simply decrement the stack pointer by 1. Okay, so this code is sort of like the opposite of this code. This pushes stuff on stack, and this pushes into and pops from the stack. Okay, so we will need these ideas in order to implement recursion, because to implement recursion we need to make use of memory, and not only that, we need to have this notion of a stack going on in memory in order to implement recursion. Okay. All right, so what we're going to do next is look at a program called factorial_rec.hmmm that calculates the factorial of a number recursively. Okay, so let's go through this program. The first thing that we do here is we initialize the stack pointer to some location in memory, some arbitrary location in memory. Okay, so you have your memory, and here is cell number 0, cell number 1, and so on and so on and so on. And then 100 is somewhere here. And we say that our stack pointer is initially pointing to that location in memory. All right. Now, this is just an arbitrary number. All that we need to make sure that it doesn't interfere with the program itself. So you don't want to pick a lower number that sort of coincides with the program, because keep in mind, and this goes back to the previous lecture, the program basically sits in memory. So this very program, factorial_rec.hmmm, sits right here. Okay, so this is factorial_rec.hmmm. So the program sits right there. So you don't want your stack pointer to interfere with the program itself. Okay, so just pick an arbitrary location that is high enough so that it doesn't interfere with your program. All right, so that's the first line. And then what we do is we read a number, the number n, into register R2. That's our input. And then we simply call a function that's defined at 5. So this is the recursive factorial function. We'll talk about that in a bit. Now, when you do this, what is the value of R14? Well, R14 is going to be 3. Right? So this function calculates the factorial of a number and places the result in R1. Okay, so that's what the function does. It expects the input to be in R2 and the result is in R1. Okay, so when the function transfers control back, R1 has the factorial of n, which is what we write, and we halt the program. So the main part is rather simple. Now let's talk about the recursive part. Okay, the first thing that we do here is check if n is 0 or not, because n is stored in R2, and we check if it is 0 or not. If it is 0, we jump to 18. Okay, and that's basically the base case of the factorial function. So if n is 0, what we do is we jump here, and here we simply set the output register R1 to be 1, because 0 factorial is 1, and we simply return to the caller. Okay, by saying jump R14. So let's now take, before continuing, let's take an example where R2 was set to be 0. So the user supplied the value 0. So we call the function with the argument, we call the function with R2 equals 0. So what happens here? Well, R2 is 0, so we jump to 18, we set R1 to 1, and we jump to R14. But what was R14? R14 was precisely 3, so we jump here and we write the value of R1, which is 1. And that is correct because 0 factorial equals 1. Okay, so things work correctly when n is 0. Now, what if at this stage n was not 0? So we are not in the base case yet. So this is where we need to make a recursive call to factorial of n minus 1. So what do we do? Well, the first thing that we do is we increment the stack pointer by 1, okay, and then at that location we store the value of R2. What is in R2? Well, it's n, right? So we store n in memory at the location given by the stack pointer. So you have your memory, and then you increment the stack pointer by 1, and at that location you store simply the value of n. Okay, so that's this line here, and then you increment the stack pointer further by 1. Okay, that's this line, and then at that location you store the return address. Okay, and that's where the recursive call needs to return back to. Okay, so here you simply store the value of the return address, and then you decrement the value of R2, meaning n, by 1. So R2 is now n minus 1, and now comes the recursive call. So this is a call to a function who's defined at 5. Well, that is the factorial function itself. So this function is basically calling itself. All right, and when this line is executed, notice that R14 has the value of 12. Okay, so we make a recursive call, but this recursive call is now on a smaller input. It's basically f of n minus 1. All right, smaller input. N minus 1 is what we just calculated. All right, so R2 now has n minus 1 in it. Okay, so that's the recursive call. Now, when this recursive call returns, okay, where does it return? Well, it returns right here, because that's the call right after the call instruction, call and instruction, right? So it returns here. And what do we do in that case? Well, we fetch the return address from the memory, so which is this guy here, store it into R14. And then what we do is we decrement the stack pointer by 1. So that's that. And then we load whatever is on top of the stack into R2. Okay, so what was on the stack? Well, it was n, so we load it into R2. And then we decrement the stack pointer further by 1. So the stack pointer now points there. And then we perform this multiplication. Take the value in R1, which was basically the f of n minus 1, and then we take the value in R2, which was just fetched as n, and we carry out this multiplication, which is n times f of n minus 1, and that is stored back into R1. Okay, so R1 simply calculates n times factorial n minus 1. All right. Okay, again, just to recap. So when we fetched, when the recursive call returned, we end up here. The first thing that we do is fetch the return value, and then we fetch the next value into R2, which was n, and then we simply multiply whatever is in R1, which was the factorial of n minus 1, with whatever is in R2, which is n, to get n times factorial of n minus 1, and we store that result back into R1, the output register. Okay, and then finally we jump to the caller. Okay, all right. So that's how the factorial function is implemented recursively. Okay. I know this is somewhat tricky, but what we're going to do next is carefully trace this program on a small input, and hopefully that will make this very clear. And hopefully that will clarify things and show you clearly how the recursion works. But before that, here is an output of the program. So after you assemble this program into factorial_rect.b, you run it using this command. And when you do that, the program expects an input n. Let's say you type 5, and the program comes back with 120, which is indeed 5 factorial. So now, what we're going to do next is carefully trace the recursive factorial function on a very small input, such as n equals 3. Okay, and we know that here 3 factorial is simply 3 times 2 times 1, and that is 6. Okay, and 6 is what we eventually expect to see in the register R1, and the input 3 is in register R2. Okay, so let's see if that works out. Okay, so here I'm showing you the code for the recursive factorial function, and here is a trace, all right, as the function evolves. Now, remember when we call the function, we called it with R15 set to 100. Okay, so the stack pointer is pointing to the location 100 in memory, right? And when we jumped into the factorial function from the main part, R14 was had the value 3, okay, because that's the instruction that immediately follows call n. So that's 3. And then the input to the factorial function is an R2, which is we said is the number 3. That's the number for which we want to calculate the factorial. All right. So the first instruction that is executed is this guy here. Is R2 equal to 0? Well, it's not. It's 3. So the next instruction that executes is 6. So what does 6 do? It simply increments the stack pointer R15 by 1. So R15 now becomes 101. All right. And then we store the value of R2 in R15. What was in R2? It was 3. So that's what you see in 101. Okay. And then we increment R15 again by 1, so that becomes 102. And then we store the return address R14 in R15. But what is in R14? Well, it's the number 3, so 3 is stored in 102. Okay. The next thing that we do is decrement R2 by 1, so R2 becomes 2. And then we make a recursive call to the factorial function. So that's line number 11. But when we do that, what ends up in R14 is 12. So that's how you get this 12 in R14. Okay, and we jump back to the function, which is instruction 5. Okay, and at 5, what do we do? Compare R2 with 0. Well, it's not 0. So the next instruction is instruction 6. We add 1 to the stack pointer, so that becomes 103. We store R2 there. So at 103, we end up getting 2. And then we increment the stack pointer again by 1, so it's 104. We store the return address there, which is 12. And then we decrement R2 by 1, so that now becomes a 1. And then we make another recursive call to the factorial function. So here again, R14 is going to be 12, because that's the instruction that immediately follows instruction 11. Okay, so that's that. And so that's a recursive call. We are back in instruction 5. We compare R2 with 0. It's not 0. So the next instruction is 6. We add 1 to R15. So that's 105. We store R2 there. So that's that. And then we increment R15 by 1. So that's 106. Then we store the return address there, which is again a 12, because that's what was in R14, right? And then we decrement R2 by 1, so R2 now becomes 0. and then we make another recursive call. So here again, R14 is going to be 12, and we jump back to 5. But now notice that R2 is 0. So what do we do? The next instruction, so when R2 is 0, the next instruction is 18. And what do we do in instruction 18? Well, we set R1 to be 1. So that's what we see there. And then we jump R to R14. But what was in R14? Just check. It was 12. So we jump unconditionally to 12. And what are we doing at 12? We load whatever is in the location given by R15, which was 106. And that location had the number 12. We load that into R14. That's the return address. Okay. And then we decrement R15 by 1. So it now becomes 105. Then we load whatever is in that location into R2. So R2 is now 1, because that's what was in memory at the location 105. And then we again decrement R15 by 1. So that now becomes 104. And then we multiply whatever is in R1 with whatever is in R2 and store the result back in R1. Well, R1 has 1, R2 has 1, their product is 1, we store that result in 1. Okay? And then we jump to R14, but what was in R14? It's 12. So we jump back to 12, and then in 12 we repeat the whole thing. We fetch whatever is in location given by R15 into R14, so that's 12. And then we decrement R15 by 1, it becomes 103. And then we load whatever is in that location given by R15 into R2. So we get a 2, it comes from here. And then we decrement the stack pointer again by 1 to now get 102. And then we multiply whatever is in R1 with whatever is in R2 and store the result back in R1. So 1 times 2 is 2, which we store in R1. And then we jump to R14 unconditionally, but that was a 12. So the next thing that we execute is 12 again. We fetch something from location given by R15 into R14, but now notice that that was 3. So R14 now contains 3. Okay, that's the return address. Okay, we decrement stack pointer by 1, so that becomes 101. We load whatever is in the location given by R15 into R2, but that's 3. That's what we store in R2. Now we decrement stack pointer again by 1, which becomes 100. And now we multiply R1 and R2, so 2 and 3 to get 6, which is stored in R1. Okay? And then finally, we do a jump R of R14, but now notice that R14 had the value 3. So you're out of the recursive function and you're back into the main part at instruction 3. And if you go back to the previous slide, you'll see that at that instruction, we simply write R1. So that ends up writing the value 6. And that is indeed factorial of 3. Okay, so that's how the recursion unfolds, right? So I hope it's clear at this point on how recursion works. Okay, so the last bit then is to just look at the entire HMMM instruction set, right? So you have what are called system instructions, and we have seen all of these. We have seen the halt instruction. Read is what you use to read user input into the register RX. Write is what you use to write output. So it simply writes the value of that register. No op does nothing whatsoever. It's just a filler. Okay, and then here are all the instructions that you use to set register data. This sets the register RX to a number n from this range. This one adds this number to the value in this register, and this number n is from that range. If n is negative, you're decrementing the register value. If n is positive, you're incrementing it. Copy is what you use to copy this register's value into that register. And here are the arithmetic instructions. You add these two guys together to store the value in this register. This instruction subtracts rz from ry and store the result in rx. This one negates the value in ry and stores the result in rx. Multiplication multiplies these two guys and stores the result in rx. Division divides these two registers, stores the result in rx. Mod is what you use to calculate the remainder of ry and rc. So for example, if mod, so let's say you have mod r3, r2, r1, and if these registers have the value, let's say 11 and 3, what is going to be in r3? Well, it is the remainder of 11 and 3, which is simply 2. All right. Okay, and then you have jump instructions. So these two are unconditional jumps. Here you jump to an instruction number. Here you jump to an instruction number that sits in this register. Okay. These are all conditional jumps. So you jump to n if this register is identically 0. You jump to this instruction if this register is not 0. You jump to this instruction if this register is strictly greater than 0. And you jump to this instruction if this register is strictly less than 0. And here is the instruction that you use to call a function whose definition starts at n. And when you do that, the return address, which by convention is r14, will contain the following instruction number. Okay, the instruction that follows call n immediately. And then you have these instructions to interact with memory. You can load the value in memory at this address into this register. You can store the value in this register at that location in memory. And then here, what you do is you load a value from the memory location that is given by this register into this register. So the memory location is given by a register here. And then here, what you do is you store this register value at a location that is given by this register. Okay, so this register has a memory location. It's at that memory location that you store the value of the register Rx. Okay, so that's the entire instruction set for HMMM. All right, so that concludes this lecture. Thank you for watching.